So let us start this discussion with the reference of a signal x of t, which looks something like that. A signal x of t, which is existing from t1 to t2. So it is quite obvious that the signal is an aperiodic signal. So it doesn't get repeated. A bound is there, time bound is there, time limited signal. There is no periodicity, or you can also consider that the periodicity is equal to infinity. If I extend t1 towards minus infinity towards plus infinity, something like that. So that is a signal at our hand, and we would like to know what are the different frequency components present within that particular signal. So while we have discussed the notion of the vector space representation of signals, we have mentioned that for the periodic signal, a signal which is having a fundamental period of say T naught, then there could have been a number of such frequency components present within that particular signal, which are known as the fundamentals as well as the harmonics of the signal. So, for example, we started with e to the power j omega naught t, and then we have obtained the other harmonics, the higher order harmonics like e to the power j twice omega naught t, e to the power j thrice omega naught t, e to the power j 4 times omega naught t, and so on and so forth. So these are the different frequency components, or rather, these are the different signals, and the presence of those signals in the actual periodic signal we have also obtained. Now here the situation is something different. Here we find that the signal itself is aperiodic, and so we don't have any limitation on finding out the frequency of the signal. The complex rotating phasor that we are considering over here is e to the power j omega t, where omega can range from minus to plus infinity. So therefore we can consider all the frequencies from minus to plus infinity, and we can find out the frequency content present within that particular signal. So that can be done very easily by virtue of the inner product or dot product. And already we know what is meant by the inner product. The signal x of t, when it is, you have this signal x of t, and if you just calculate the inner product between the signal x of t and this e to the power j omega t, that will give us integration over minus to plus infinity x of t to the power minus j omega t dt. So here we have this integration sign because x of t is a continuous time of signal, and we consider all the frequency components from minus to plus infinity over there. And this is a kind of representation where the vector space dimension is uncountably infinite. So it can be countably infinite or uncountably infinite. So for a periodic signal, we have noticed that the number of frequency components present within the signal is countably infinite, like omega naught, twice omega naught, thrice omega naught, 4 omega naught, 5 omega naught, and so on and so forth. So plus minus k omega naught, where k can range from minus to plus infinity. But here, the range of the signal, it can assume the range from minus to plus infinity and all the real numbers. So there we have like k times omega naught, where k was like the numbers, the natural numbers, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. So they are also infinite, but countably infinite. But here we have the uncountably infinite. So this set is a little bit larger as compared to the previous set. Anyway, so in that case, we have to consider the integration instead of summation, and that value, integration from minus to plus infinity x of t e to the power minus j omega t dt, gives us the inner product between the signal x of t and this complex rotating phasor e to the power j omega t, and that value is equal to x of j omega. So what is that x of j omega? This is the component of xt along this complex rotating phasor e to the power j omega t. So that is derived from the notion of the vector space representation. And mathematically now we can give a name to it, and that particular name is given like the Fourier transformation of the signal x of t. Remember that Fourier transformation is applicable when the signal is aperiodic in nature. If the signal is periodic in nature, then you have to go for a Fourier series representation that we have done previously. And if the signal is aperiodic in nature, then the signal is represented in the frequency domain by virtue of the Fourier transformation of the signal. So the name is given by famous French scientist, mathematician, Joseph Fourier, named after him. So now the question is that once you get this x of j omega, as the component of xt along e to the power j omega t, and that's a different types of representation. So here the signal is represented in the time domain, and there the signal is represented in the frequency domain. Now the question is that if you have these different components of xt along e to the power j omega t, can you derive the original signal back from these frequency components? That is the question. So what I want to mention over here is you have a vector, the vector v is there, and here I have, for the sake of clarity, I have just used a two-dimensional vector. The vector v is there, and we have two different unit basis functions u1 and u2, and we'd like to find out the component of this v along u1 and u2. So v1 is the component of v along u1, this unit vector, and v2 is the component of v along u2. So we have already derived those components v1 and v2. The question is that can I reconstruct the vector v from v1 and v2? Yes, we can do that. If we know the corresponding components, and if you know the basis vector through which these components are derived, you can very easily calculate, or rather we can very easily reconstruct the signal, the vector v, by virtue of v1 u1 plus v2 u2. So v1 is the component of v1. This v1 is the component of v along u1, and v2 is the component of v along u2. So the expression that we have just now derived, x of j omega, that is equal to minus to plus infinity x of t e to the power minus j omega t dt. This is also known as the continuous time Fourier transformations, because the signal xt is continuous there. Similarly, you can also have a discrete time Fourier transformation where the signal x of n varies in a discrete fashion. It can assume only discrete values along the n axis, and that time it is known as the discrete time Fourier transformations. And you will study a lot about this discrete time Fourier transformation in some later course in digital signal processing. Now here in this particular course on signals and systems, I would like to restrict my discussion into only continuous time Fourier transformation. So once you get these frequency components x of j omega, like these v1 and v2, these are the components. The question is that how can I reconstruct the original signal back? Reconstruction is possible if I know the frequency components, if I know the corresponding components, and if I know the corresponding unit vectors, the basis vectors through which these components are derived. So here x of j omega is the corresponding component along e to the power j omega t. Just like that, here you have like v1 along u1, v2 along u2. We have reconstructed the signal like v1 u1 plus v2 u2. Similarly here, x of j omega is the component of this x of t along e to the power j omega t. So you just take it, x of j omega, and multiply it with the corresponding components e to the power j omega t, and then you go for a summation. So this summation is basically the accumulation. This is basically the integration. So here you don't have a summation, because here the dimension is equal to, infinite dimensional vector we are considering there. So instead of considering the summation, we have to go for an integration. So integration over minus to plus infinity x of j omega e to the power j omega t d omega. Now this is known as the inverse Fourier transformation. So from forward Fourier transformation or from simple Fourier transformation, we can get the frequency components of the signal, and from the inverse Fourier transformation, what we can get is we can reconstruct the signal from its frequency components. Now, one thing to be noticed here is that you have some additional factor present outside this integration sign, that is 1 by 2 pi. Now, this is taken over there to take into account that ultimately the basis vectors that we are considering, so these basis vectors should be orthonormal basis vectors. So, to ensure that the basis vectors that we are considering altogether, they are the orthonormal in fashion. So some constant part is multiplied to make it, or to ensure that this x of t is properly obtained from its frequency components. In some of the literature, you can also find that this x of j omega, in the expression of x of j omega, 1 by root 2 pi is there outside, and in the expression of x of t, 1 by root 2 pi is there. So this 1 by 2 pi is divided by like 1 by root 2 pi and 1 by root 2 pi. And some of the literatures, in most of the literatures, you'll see that this 1 by 2 pi, this constant is there outside the inverse Fourier transformation expression. However, if we make it a simple, instead of considering the angular frequency, if we consider the Hertz frequency, f frequency, then it will be much more easier to correlate. This x of f can be represented like minus to plus infinity x of t to the power minus j twice by ft dt. So this omega is represented like j twice, this omega is represented like twice by f. Omega is the angular frequency and f is the Hertz frequency. So this expression of x of f can be represented like integration over minus to plus infinity x of t to the power minus j twice by ft dt. That is the expression for the forward Fourier transformation. Now, when I get to have the reconstruction part, this reconstruction is given by x of t, that is equal to 1 by 2 pi integration over minus to plus infinity x of f e to the power j twice by ft, and in place of d omega, what I can write is twice by df. Now this twice by gets cancelled from this side and that side. So then ultimately this x of t is integration over minus to plus infinity x of f e to the power j twice by ft df. So it looks pretty simple. I mean, this x of f expression and x of t expression pretty simple when you consider the frequency as the Hertz frequency instead of the angular frequency. So here we have mentioned both of these two representation, x of j omega that is equal to minus to plus infinity x of t e to the power minus j omega t dt, and x of f is equal to integration over minus to plus infinity x of t to the power minus j twice by ft dt. Now, what about the corresponding inverse Fourier transformation for the second representation? This inverse Fourier transformation x of t can be represented as minus to plus infinity x of f e to the power j twice by ft df, as you know it very clearly. Now, we do a kind of substitution over here in this particular expression. What we do is here, like x of f is equal to minus to plus infinity x of t e to the power minus j twice by ft dt. Now in this expression, we just replace f by t. So whenever we have f, we replace it by t. The variable change we are making over here. So it becomes capital X of t there, the left hand side, right hand side minus to plus infinity, small x. Then in place of t, we place f there. Then e to the power minus j twice by ft dt. It will be to the minus j twice by tf df, something like that, or e to the minus j twice by ft df. So we have just changed this notation. So whenever we find f in the expression, we make it t, and whenever we find t in the expression, we make it f. So why we have done so? Then after that, after we get this one, this expression minus 2 plus infinity x of f e to the power minus j twice by ft df, then we do another substitution, that is we substitute f by minus f. If you substitute f by minus f, so nothing gets changed in the left hand side, because in the left hand side we have only x of t, capital X of t. The right hand side we have some change. This x of f will become x of minus f there. E to the power minus j twice by ft will become e to the power plus j twice by ft there, and this df will become minus df. So whenever it is minus df, so there will be a minus sign outside, and we can absorb in the limit. Then the limit remains the same, minus to plus infinity x of minus f e to the power j twice by ft df. Now if you compare these two expressions, this one which are written in the blue, this one and this one, here you see x of small x of t is equal to integration over minus to plus infinity x of f e to the power j twice by ft df, and here we find this capital X of t is equal to integration over minus to plus infinity small x of minus f e to the power j twice by ft df. So this is an inverse Fourier transform expression. It suggests that from the first expression, this expression suggests that this small xt and capital Xf, they form a Fourier transform pair. Small xt is there in the time domain and capital Xf is there in the frequency domain. So this small xt and capital Xf, they form a Fourier transformation pair. And in the second expression, what we find is that this capital Xt and small x of minus f, they form another Fourier transformation pair. So capital Xt and small x of minus f, they form another Fourier transform pair. And this particular property is known as the duality property. And this is very, very useful whenever you go for calculating the Fourier transformation of some complicated signals. So it suggests that if you know the Fourier transformation of any signal x of t, the small x of t means a particular type of signal, and capital X of f is another type of signal in the frequency domain. So if you know this particular property, duality property, then it will be very, very useful for you to find out the Fourier transformations without going into the detailed calculation. So with the help of a reference example, you'll be able to understand the concept in a much more elegant way. Now let us assume that we have a get function, and the get function is defined like this. This get function is defined in the time domain from minus t naught to plus t naught. This x of t is defined. Once again, another aperiodic signal. It is defined from minus t naught to plus t naught. with an amplitude equal to 1, and that is equal to 0 outside. So as you understand, it's a completely time bounded signal, minus t naught to plus t naught. And we are trying to find out its corresponding Fourier representation, a frequency domain representation. This x of j omega we are calculating, that is given by minus to plus infinity x of t e to the power minus j omega t dt. That is the formula for the forward Fourier transformations, continuous time Fourier transformation. If you just substitute this value, x of t is equal to 1 from minus t naught to plus t naught, and rest of it is 0. So we just integrate from minus t naught to plus t naught. It is 1, amplitude is 1, then e to the power minus j omega t dt. That gives you e to the power minus j omega t by minus j omega minus t naught to plus t naught. And then if you do the calculation, then ultimately what you are getting is twice t naught sine omega t naught by omega t naught, where omega is the corresponding angular frequency given by twice by f. So that is a representation in terms of the angular frequency. You can also represent the same thing in terms of the Hertz frequency. So this Hertz frequency representation is something like that. X of f is given by twice t naught sine twice by f t naught by twice by f t naught. Now last day we have mentioned that any signal which is represented in this form sine pi x by pi x, this is the form of a sine c function. So here x value is equal to twice f t naught. So sine twice by f t naught by twice by f t naught will give you sine c twice f t naught. So ultimately this expression becomes x of f, that is equal to twice t naught sine c twice f t naught. So if you have the signal x of t in the time domain, something like that, ranging from minus t naught to plus t naught with an amplitude equal to 1, then in the frequency domain, it gives rise to a sinc function that is equal to 2 t naught sine c twice f t naught. How do they look like? If you just take a look at the appearance of the signal in the time domain looks something like that, x of t, which is ranging from minus t naught to plus t naught with an amplitude equal to 1. And in the frequency domain, the value equal to twice t naught sine c twice f t naught. So as you know, for a sinc function, there are certain properties we have already mentioned during the Fourier series representation, that sine cx, that is equal to 1 when x is approaching towards 0. At x is equal to 0, this sine cx is equal to 1. And for all other integer multiples of x, sine cx will be equal to 0. So here the value inside this sine c function is twice f t naught. So whenever you have this twice f t naught is equal to plus minus 1, plus minus 2, plus minus 3, and so on, then the value of this x of f will become 0. So these are known as the zero crossing points, right? So if twice f t naught is equal to plus minus 1, plus minus 2, plus minus 3, and so on, then the corresponding frequency values are given by plus minus 1 by 2 t naught, plus minus 2 by 2 t naught, plus minus 3 by 3 t naught, and so on. So here this is the 0 point, zero frequency. At zero frequency, sine c function will give you 1. So the magnitude becomes twice t naught, this one. That is the magnitude of the sinc function. And at every integer multiple of twice f t naught, this is value equal to 0. Accordingly, you have to calculate what are those f values. These f values are plus minus 1 by 2 t naught, plus minus 2 by 2 t naught. That means here the first zero crossing 1 by 2 t naught, the second zero crossing 1 by t naught, the third zero crossing, here you have like 3 by 2 t naught, and so on and so forth. Here also you have like minus 1 by 2 t naught, minus 1 by 2 t, minus 1 by t naught, then minus 3 by 2 t naught, and so on and so forth. So at those frequency points, the xf value will become 0. Otherwise, this xf will be in between 2 t naught and some fixed values over there. And this particular, the first zero crossing, minus 1 by 2 t naught to 1 by 2 t naught, this first zero crossing is known as the main lobe of this particular sinc function. And as you increase the frequency, the amplitude of this particular height gets reduced, and ultimately it will extend up to plus infinity in this direction and minus infinity in that direction. So accordingly it will move. So what I find is, if I have a signal like this in the time domain gate function, then its frequency domain representation is a sinc function, and that sinc function looks something like that. Now, why I have used that particular example for the demonstration? The thing is that suppose you are asked to, it is very easy to calculate the Fourier transform of this kind of signal, a gate function. It's pretty simple. It's a constant function from minus t naught to plus t naught, and you can very easily calculate, you can very easily integrate the signal from minus t naught to plus t naught and calculate the corresponding Fourier transformation. Now suppose you are asked to find out the Fourier transformation of this kind of signal, which is defined in the time domain, not in the frequency domain. This x of f here, it is defined in the frequency domain, but suppose instead defining it in the frequency domain, suppose this x of t is defined in the time domain, like so. Y of t is equal to say a sine c of t from minus to plus infinity. So that is the definition, and you are asked to calculate the Fourier transformation of the signal. Now it is very cumbersome to calculate the Fourier transformation of this signal, because the sinc function and you have sinc there sin c function multiplied with some e to the power minus j twice by f t df and all these things. So ultimately it is very difficult for you to calculate the Fourier transform directly if you are provided with sinc function as your signal in the time domain. Now here this duality property will help us. Duality property says that if you know this Fourier transform pair xt and xf, that means here small x is the get function and capital X is the sinc function. So get function and sinc function, they form a Fourier transform pair. So now if you just reverse the role of this gate, and so here the gate is defined in the time domain and sinc is defined in the frequency domain, and you are asked to find out the frequency domain representation when the signal in the time domain is not a get function, rather it's a sinc function. So get in the time domain will give you sinc in the frequency domain. So sinc in the time domain will give you the gate in the frequency domain with a mirror image, because you have like x of capital X of this one, capital X of t and small x of minus f. So you have a mirror image over there. Now that doesn't affect in this particular case because the signal is symmetric with respect to f is equal to 0 axis. So since the signal is symmetric, so it doesn't affect obviously in this particular case. Now since it is sin c t, and to make it simple, we just assume that twice t naught is equal to 1. If twice t naught is equal to 1, in that case this function becomes like x of f is equal to sin c of f, something like that. So you are asked to find out sin c of t. So pretty simple, you make it like you just invoke the duality property and you find out y of f. So y of f is given by this particular get function in the frequency domain, and the frequency is like, I mean the range is from minus half to plus half only. The range is from minus made like twice t naught is equal to unity, and here it was like minus t naught to plus t naught, so it should be minus half to plus half. Okay, and here you have some magnification by a factor outside. So as you know that just like a Fourier series, Fourier transform also follows the linearity property. So here we can invoke the property of homogeneity. So since this yt gets multiplied with a, so here also this yf gets multiplied with a, and even if you make it this is yf, this is also yf minus f, because this get function is symmetric with respect to f is equal to 0 axis. Now moving further, what we have obtained as of now, get function and sinc function, they form Fourier transform pair, and from that we can obtain, or we can identify a very important property of Fourier transformation. Now we have when we have calculated the forward Fourier transformation, there we have noticed that the get function is time limited and this sinc function is band unlimited. That means the get function is defined over minus t naught to plus t naught, but the sinc function is defined over all the way from minus to plus infinity in the frequency domain. And now, if you invoke the duality property, it says that the duality property, the sinc function is time unlimited. It is like a sine ct for all t ranging from minus to plus infinity. And here, the get function becomes band limited. So if the signal is time limited, then it becomes band unlimited. And if the signal is band limited, the signal should be time unlimited. So it's a very important observation for any kind of signal, because most of the signals that we deal with in the practice, these signals are typically they are time limited signal, because we don't have like time unlimited signal, because that is a kind of hypothetical notion that signal will extend for all the way from minus to plus infinity. So theoretically, hypothetically is possible, but practically is very difficult. For all the signals, they are time limited. They must have some time bound, say few seconds, few milliseconds, or few minutes, or few hours. It cannot extend towards. I mean, it cannot exist for a time range which can extend from minus to plus infinity. So most of the signals are time limited, so they should be band unlimited. And if you find some signals which are time unlimited, which are some, I mean, they are not the practical signals, some very idealistic signal like a sinc function or sinusoidal functions, for example, which exist for all the time, which are time limited, then it should be band unlimited. So time limited means band unlimited. Signal is time limited, that means it is band unlimited. And if the signal is time unlimited, then it should be band limited. Now let us take a look at some of the properties of Fourier transform as well as we have done for the Fourier series. So the first property says that if the xt is a real signal, most of the case if the signal is a real signal, that means x of t is equal to x star of t. If you take the complex conjugate of xt, it will give you the same signal. Then what is the relationship in the frequency domain? So if xt is equal to x star t, then x j omega is equal to minus to plus infinity x of t to the power minus j omega t dt. What about its complex conjugate, this x star j omega? That is given by minus to plus infinity x star t to the power j omega t dt. You just take the complex conjugate of the whole thing, whole integrand. Now, since the signal x star t and xt they are same because xt is a real signal, so therefore I can write in place of x star t, I can simply write x of t e to the power j omega t dt. Now, what is that? X of t e to the power j omega t dt. Basically, this is the Fourier transformation of, in the expression of x of j omega, we find that this is minus to plus infinity x t to the power minus j omega t, and this expression says that x of t to the power plus j omega t dt. So only one change should be there, that is x of minus j omega. So x star j omega is equal to x of minus j omega. So both of them, x j omega, this particular thing, x j omega and x minus j omega, they are the complex numbers. They have their real part and they have their imaginary parts. And if x star j omega is equal to x of minus j omega, that means this signal x of j omega is a complex conjugate symmetric. So therefore, the real part of x j omega is equal to the real part of x of minus j omega, which suggests that the magnitude spectrum is an even function of the frequency. And this imaginary part of x j omega is equal to minus of imaginary part of x of minus j omega. That means the space spectrum is the odd function of the frequency. Now that is true when the signal is real in nature. Now sometimes the signal is real as well as the signal is even also. That means xt is equal to x star t, that is also x of minus t. So in that case, if you just calculate this expression, what you get, you find that it looks something like this. X star j omega is equal to minus 2 plus infinity x star t to the power j omega t dt. And in place of x star t, you can also write x of minus t. Then you do another substitution over there. Let's put tau is equal to minus t, that means tau is equal to minus dt. Then this integration will be from minus to plus infinity x tau e to the power minus j omega tau d tau. So it is simply the x of j omega. It is no longer x of minus j omega, rather x of j omega. So here we find if the signal is real as well as even, signal in the time domain, then x star j omega is equal to x of j omega, and that is only possible if x of j omega is a real value, otherwise not possible. And the perfect example that we have seen for this one is the example of the get function, because for the get function the signal is real, there is no complex part, it is 1 from minus t naught to plus t naught, and this is also even because the appearance of the signal in the positive direction and the appearance of the signal in the negative direction being the same. So we have also noticed that in that case x of j omega is also real value, because what we get in place of x of j omega or x of j f, we get it like a sinc function, that is a real valued signal. So these are the properties, and the description, the demonstration or the example is that here you have used this property and that property. This duality property is known as the symmetricity property. We have also discussed the symmetricity property in the Fourier series representation as well. And perhaps you have noticed that both of these two properties can be well explained. Symmetricity property and duality property can be well explained if I take this get function as my uh, reference signal for the demonstrations. That's why I have used this get function, because if I take the get function, then I'll be able to explain the notion of the symmetricity properties as well as the duality property by using only one example itself. Now, before I conclude, I would like to give you another important property associated with the Fourier transformation. So as you know, we have like an LTI system. Now let's from the signal perspective. Now let's move to the system perspective as well. Now we have some LTI system which is characterized by its impulse response, and that impulse response is given by h of t in the time domain. And suppose xt is the signal that you'd like to provide at the input of the system, and we'd like to get the output yt, which is simply the convolution between xt and ht. That is quite obvious. We have already discussed this in the previous units, that if I provide xt as my input, then the output yt is given by the convolution between xt and ht, if and only if the system is LTI. If the system is non-LTI, then you cannot write this yt as xt convolution ht. But if the system is LTI or LSI, in that case only you can represent yt as xt convolved with ht. Now, that is the scenario in the time domain representation. Now let us do the same thing. Let us observe the same thing, but from a different perspective. So this perspective matters now. Now, whenever we discuss this Fourier series and Fourier transformation, that means we are dealing with the same signal, but the paradigm shift is there. We are observing the signal from a different perspective altogether. So x of t, as you know, suppose x of t is some aperiodic signal. Say, suppose it extends from say minus to plus infinity. Aperiodic signal. The signal is present. Now we are not observing the signal xt as xt itself. Rather, we are observing the xt as the appearance or the accumulation of the different frequency components along with their components. So now this x of t, now we are observing that this x of t, they have this particular signal. It consists of a number of frequency components, like along the different complex rotating phasor. So e to the power j twice by ft is one such complex rotating phasor along with its component. So whenever we apply x of t, now I'm not visualizing x of t alone, rather I'm visualizing x of t as the constituent part of x of t is x of f e to the power j twice by ft, something like that. And the LTI system is observed in the frequency domain as well, like h of f. Now when I provide this kind of input, x of f e to the power j twice by ft, to an LTI system which is having its frequency response h of f, which is nothing but the Fourier transformation of its impulse response. H of f is nothing but the Fourier transformation of its impulse response h of t. And suppose any arbitrary frequency I'm providing, any arbitrary frequency within the minus to plus infinity range, any arbitrary frequency f is being provided over there, and the corresponding component of this x of t is given by x of f. So basically what we are providing, what we are feeding to the system, we are feeding to the system like x of f e to the power j twice by ft. And we know that h of f is the frequency domain representation of this particular system, or the frequency response of this particular system. Now once I provide this, what we are supposed to get? I'm supposed to get this original signal back. That is the notion of the eigenfunctions or eigenvalues. I provide the original signal back. I give this signal x of f e to the power j twice by ft is a complex rotating phasor along with some constant factor, the component. Now since it's a e to the power j of twice by ft, the complex rotating phasor, so I'll be getting this back. I'll be getting this back multiplied with the value of this h of f at this particular frequency. So I can also consider, say, or any frequency, any arbitrary frequency, it is possible. So I'll be getting this back x of f e to the power j twice by ft multiplied with the value of this hf. Right. Now this is what? This is basically the output of the LTI system. Now, if I look at the output, so as of now we have looked at the output as output itself in time domain y of t. But now we can also visualize the output as the appearance of different frequency components e to the power j twice by ft along with their corresponding components y of f. So it should be basically y of f e to the power j twice by ft. And since we are getting the same output, one from the perspective of this application of input and the system performance, and one from the characteristics of the output itself, so this should be similar, or this should be equivalent. So then what I can infer is this y of f must be equal to x of f into h of f. If I observe y of t alone, So I know that whenever I get y of t from this LTI system output, this y of t is visualized in the time domain. This is visualized in the time domain, and this is visualized in the this y of f is visualized in the frequency domain. So both of them are equivalent. So convolution operation in the time domain is equivalent to multiplication operation in the frequency domain. And we can also prove this. We can also prove this mathematically. So that is a kind of analytical expression that we have used last slide. And we can also prove this mathematically. So y of t is equal to xt convolved with ht. So that is expression of the convolution. And ht minus tau can be represented like minus 2 plus infinity h of f e to the power j twice by ft minus tau df. And from that we can calculate or we can simply substitute the value of h of t minus tau in this expression. This gives rise to this one, and then what I get, do some kind of modification, simple substitution. This value will give you like x of tau e to the power minus a twice by f tau d tau will give us x of f there, and the rest part is untouched, h of f e to the power j twice by ft df. Then this is basically x of f, this is h of f, then e to the power j twice by ft df. And we know that y of t is basically minus 2 plus infinity y of f e to the power j twice by ft df. Both of them are equivalent. So therefore, y of f is equal to x of f multiplied with h of f. So the analysis that we have made in the last slide, so there is an analytical observation and this is a mathematical observation, and both of them satisfy each other. So with this, we have come to the end of this Fourier transform representation of aperiodic signal. And so over the last few lectures, we have discussed about the Fourier series representation for the periodic signal, Fourier transform representation of the periodic signal. And before I conclude, I would like to mention that the Fourier series and Fourier transforms, so these are particularly the visualization of the signal from quite a different perspective. We are observing the signal, but not from the time domain perspective, but from the frequency domain perspective. So with this, I would like to conclude this lecture.